Hey everyone. So in this video, I like to talk about transformations of functions. Specifically, I like to focus on shifts and reflections. So, we've been dealing with graphs of functions for a little while now, but we really have only seen the graphs of a handful of specific kinds of functions, right? We're familiar with the graph of f of x is equal to x squared, f of x is equal to the absolute value of x. We have, a list of common functions that we've been referring back to again and again. And so, there are many functions out there that can be viewed as slight variations of these common functions that we've been working with. And I like to call these slight variations transformations. And so knowing how these variations or these transformations influence our graphs will help us determine new graphs from old ones. And so here, what I really want to focus on is exploring how the graphs of these functions below compare to the graph of f of x, some original function. And so these are examples of what I'd like to call transformations. And so let's start with this function here. F of x is equal to x squared. So I want to take a look at the graphs of the functions f of x plus 3, and we add 3 onto the end, and f of x take away 2. So how do these functions compare to the graph of f of x? Well, here, let's begin by making a table. And so hopefully you're a little familiar with the graph of the absolute value of x, but I think it might be beneficial for what we're about to say to also make a table for this function. So here, f, and this is x. So if I look at values like 0, 1, 2, 3, negative 1, negative 2, negative 3 as my inputs, well, f of x just takes the absolute value of those inputs. In other words, makes them non-negative. So right, this is 3, 2, 1, 0, 1, 2, and 3 as my outputs. And we can see these points here on our coordinate plane. So the graph of our function, f of x is equal to the absolute value of x, looks something like this. Now what about this function f of x plus 3? Well, this is really the same thing as the expression, or the function, well, f of x is the absolute value of x, and we're tacking on 3 to the end. We're adding on 3 to our f function. So that's exactly what this g function is. Right, so all we're doing is we're taking the result of our absolute value function and then adding on 3. And so what do you anticipate this will do to our graph? What should the graph of this new function g of x look like? Well, if I plug in 0, well, I'm going to take the absolute value of 0, and I'm going to add 3 onto it at the end of the day, and I'm going to get 0 plus 3 is 3. If I take the absolute value of 1, and then I add 3 onto it, I'm going to get 4. Then I'll get 5 and 6 when I input 2 and 3. Taking the absolute value of negative 1 gives me 1. Adding on 3 gives me 4. Here I get 5 and 6 as well. So the graph of this g of x function, the function obtained by adding 3 on to f of x, well, really it's just saying all of my outputs are going to increase by 3. That's what that plus 3 does. And here, if outputs are depicted by the vertical axis, right, the output of a point is the vertical position of that point. Well, adding on 3 to the output is telling us that that point is going to be 3 units higher on our coordinate plane. So here I can see the points on this new function. It's 3 units higher in comparison to my old function. Right, so here this is f of x, and this is the function f of x plus 3. So if adding on 3 to the end of our function shifted the graph of our function up 3 units, what do you anticipate subtracting 2 away from our function does? And so here, maybe just to sort of go through the same motions, this function obtained by subtracting 2 to f, well, that's the same as saying, well, f is the absolute value of x, and then we're taking away 2 from f, and so it's the absolute value of x take away 2. Well, we're going to have all the same outputs as our f of x function, except they're going to be 2 less, right? We're going to subtract away 2 after we compute the absolute value. And so what we get here is we get -2, we get -1, 0, 1, we get -1, 0, 1 here. Right? For example, if I look at this output here, right, that corresponds to plugging in -2 into this absolute value of x take away 2 function. And so taking the absolute value of -2 gives me +2, and then when I subtract 2, I get 0. So that's how we're computing these outputs. And really, we see these points as just 2 lower, right? We have 2 less in comparison for their y coordinates. So that's 2 lower on this coordinate plane in comparison to our f function. And so this is f of x take away 2. And so really the takeaway is that adding on or subtracting onto our function just directly influences the outputs, and it's just going to shift our function up or down. Really, if I have the function f of x with some constant added onto the end, it amounts to a vertical shift of this function. So how should I write this? The graph of f of x plus c is, maybe here, let me rewrite it this way. In general, f of x plus c corresponds to a vertical shift of f of x by c units. Right, so it goes upwards, shifts upwards if c is greater than 0. If we're adding some positive number onto this output of our function, and then it goes down if c is less than 0, right? If we're adding on some negative value to this function, it's going to shift our graph downwards. So when we add or subtract some number to our function itself, that amounts to a vertical shift up or down of our function. And so I want to look at now what happens when we add or subtract some value to the input of our function. So I've got this function f of x is equal to x squared, and I want to explore f of x plus 2 and f of x minus 3. And we'll look at how these compare graphically to our f function. And so, just to give us some baseline to work with, let's go ahead and graph x squared. So here, I think just like before, it might be beneficial for us to make a table here. And we might be familiar with the graph of this function, but it'll be helpful to be able to refer to these points very explicitly. Here, if I input 0, 1, 2, or 3, my function just squares these inputs, right? So I get 0, 1, 4, and 9. And then similarly, I can square inputs of -1, -2, and -3 to get the same outputs 1, 4, and 9. And so here these points appear on the coordinate plane. As so, and the graph of this function looks something like this, roughly speaking. So this is f of x. And so maybe I'll tell you ahead of time, these graphs of these functions, they correspond to horizontal shifts. So g of x, right, what does that really look like? F of x plus 2, that's taking my f function and replacing the input with x plus 2. And then squaring that. So that's my g function. And then here, my h function, really that's the same as f, with the input replaced with x minus 3. So these correspond to horizontal shifts of our f function. And I definitely encourage you to pause the video and think about, maybe guess, and try and convince yourself one way or the other. Which one do you think corresponds to a shift left, and which one do you think corresponds to a shift right? Pause the video and have a moment to think about that. Okay, so let's go over these examples together. Let's look at this g function here. So here, if I make a table for this function, g of x, I can imagine plugging in some values. Maybe I'll just plug in the same values, 0, 1, 2, and 3, -1, -2, and -3. This g function, it takes my input, it adds 2 to it. So if I plug in 0, I add 2 and then I square it. So 2 squared gives me 4. If I plug in 1, I get 1 plus 2 is 3, and I square that and I get 9. 2 plus 2 is 4. I square that and I get 16. 3 plus 2 is 5. I square that and I get 25. So already these numbers are getting quite large. If I plug in -1, I get +1 squared. I get 1. If I plug in -2, I get 0 squared. If I plug in -3, I get, what is this? This is -1 squared is +1. So here I can see that the graph of this function, well, here I get the point 0, 4, -1, +1, -2, 0, -3, 1, and we can see that if I plug in -4, I would get +4 out. And so the graph of this function looks like this. This is the graph that corresponds to f of x plus 2. And so this might feel kind of funny to you. You might have guessed, or I think it's very common for students to guess, that this will shift the graph 2 units to the right. And actually this function, this transformation, shifted the graph 2 units to the left. This addition by 2 into our input shifted our graph 2 units to the left. And we can kind of see that through our table here, that plugging in smaller values of x actually gave us the same results from our f function. Right? Because of that +2, I had to plug in 2 less to get the same, to square the same number, right? To square 0. And this was the case for all of the inputs. And so if I need to plug in 2 less to get the same outputs as my f function, well, 2 less means to the left on my number line, or on my coordinate plane. And so this corresponds to a shift of 2 units to the left. And so here that suggests to us this h of x function is going to shift our graph 3 units to the right, but maybe let's go ahead and convince ourselves that that's going to be the case. So here I'm going to make a table, I've got x, I've got h of x, and here this is, maybe just to rewrite it here, h of x is equal to x minus 3 squared. And we're anticipating that it'll shift our x squared function 3 units to the right. But let's check. So if I plug in 0, well, 0 minus 3 gives me -3, and squaring that gives me +9. If I plug in 1, taking away 3 from that gives me -2, and squaring that gives me 4. Plugging in 2, take away 3 gives me -1, squaring that gives me +1, and when I plug in 3, I get 3 minus 3 is 0, and so that amounts to squaring 0. We can keep going, and we can see that plugging in 4, I square 1, plugging in 5, I square 2. Actually, I should square 2 to get 4. And plugging in -1 is only just going to make my values sort of get larger, right? So -1 minus 3 gives me -4, brings me to 16, and -2 brings me to -5, and squaring that gives me +25. So we can see that we need to plug in values that are 3 units larger to see that we're squaring the same values we saw for our f of x function, right? To square 0, I needed to plug in 3. To square 1, I needed to plug in 4, or +2. Right, so here, this amounts to shifting our graph 3 units to the right. And the graph of our function looks something like this. Right, so if I need to plug in larger values to get the same output, then really I need to look at values to the right, further right on my coordinate plane, to see the same outputs, to see the same sort of heights, to see the same function. Okay, so this is our f of x take away 3 graph. And so in general, if I have f of x and I add c to that input, this is a horizontal shift of the graph of f of x by c units. And so this shifts the graph to the right if c is less than 0, if c is negative, if we're subtracting from our input, and it shifts the graph left if c is greater than 0, right? We saw earlier that when we had f of x plus 2 in the input, this amounted to shifting our graph to the left 2 units. And so we've seen an example of a horizontal transformation and a vertical transformation, and I just want to make a statement that'll sort of give some context. So transformations typically to the input apply horizontal changes to the graph. And that kind of makes sense, right? The input, those are usually denoted by our horizontal axis, and so if we're going to change our inputs, we're going to make changes to where points are positioned in relation to our horizontal axis, left and right. But transformations to the function to the output, these apply vertical changes to the graph. Right, so here if I'm going to make some changes, right, if I add some quantity to the result of my function, right, if I take f of x and I add something, then that's going to amount to shifting my graph vertically. And as we saw, if I make changes to my input, that's going to shift my graph horizontally. Okay, and so let's take a look at this applied to an example here. So I want to sketch the graph of g of x is equal to the square root of x plus 2, and then plus 3 on afterwards. And so if you're feeling up for this, please feel free to pause the video and try this example out yourself first. And so what I want to point out is that really I can think of this as a transformation. This function is coming from a transformation of our square root function, right? This is a transformation of f of x is equal to the square root of x. Right, there's sort of two things going on here, is that really this g of x function, well, it's f of x plus 2. Right, if I plug in x plus 2 into my square root function, I get this part here. And then really there's still this plus 3 on afterwards. Right, g of x is really the same as taking the square root function and inputting x plus 2 into it, and then adding 3 on afterwards. And so here we know that adjusting our input in this way shifts the graph left 2 units. And here this plus 3 tacked on at the end, it shifts up 3 units. And so the graph of f of x is equal to the square root of x, right? Here I have the point 0, 0, the point 1, 1, the point 4, 2. The graph of the square root of x looks something like this. And so g of x, if it's really a shift left and a shift up, well, here all the points that we see on that f of x graph, they're going to be shifted 2 units to the left and 3 units up. And so really g of x looks something like this. So there's one point, here's another point, and here's another point. This is really the graph of our g of x function. And so really we're able to just graph g of x based on our understanding of transformations and the fact that we knew one graph to start with, f of x is equal to the square root of x. So this is really a powerful idea that we can apply generally to lots of different functions. And so let's do the reverse now. Here I've got the graph of some absolute value function, right? So I can kind of think of in a similar way, this is that there's sort of a base function or a parent function is f of x is equal to the absolute value of x. And I can think of this as some transformation of f of x. Now I would encourage you to pause the video and give this example a try. Can you think of an equation for this graph here using our understanding of transformations? So here I see that this sort of tip is at the point 4, 1. And so it kind of looks like our absolute value graph, but shifted to the right 4 units and up 1 unit. Right, so here shifted right 4 units and up 1 unit. And so to shift right 4 units, I can think of, let's call this g of x is equal to f of x take away 4, right? That is the transformation we need to apply to shift 4 to the right. And then if it's going to be shifted up 1 unit, there should be this plus 1 at the end that shifts 1 unit up. All right, so g of x really can be expressed as g of x is equal to the absolute value of x take away 4 plus 1. Okay, so the next thing I want to take a look at is this idea of a reflection. And so let's start again with this absolute value of x function. So what is the graph of negative f of x going to look like? Well, here if we take our table for the absolute value of x, so here's f, here's the inputs 0, 1, 2, and 3, negative 1, negative 2, negative 3. Right, the absolute value just takes these values and makes them positive. And so the graph of this function, as we've seen already, looks like this V-shaped graph. And so what does the negative of this function look like? Negative f of x. Well, it's going to take all of those quantities and negate them, right? Take all of those results and negate them. Right, so here maybe I'll rewrite that negative f of x. This is the same thing as negative the absolute value of x. Right, so if my function is negative the absolute value of x, well, here I'm going to take the absolute value of my input. It's going to make it positive, and then I'm going to take the negative of that and make it negative again. So here's negative 3, negative 2, negative 1. We're going to take those outputs of our f of x function and negate them. And so if my outputs are negated, they're going to get flipped over the x-axis. They're going to be on the other side of the x-axis, and we can see them here. Right? So here is point 0, 0, negative 1, comma, negative 1, negative 2, comma, negative 2, negative 3, comma, negative 3, 1, negative 1, 2, negative 2, 3, negative 3, 4, negative 4. Really, all of our outputs, if they were negated, then their y value is going to get flipped to the negative value and go across the x-axis onto the other side. Right, so here, really what this negative f of x did to the graph of our function was it flipped the graph of this function across this x-axis. This is a vertical reflection of the graph. Is when we take our function and we negate it, it's going to give us a vertical reflection over the x-axis. So what if we start with f of x is equal to the square root of x, and we want to find what the graph of f of negative x looks like if we negate the input now of this function? Well, here, let's again make a table. So here I've got x and f of x. And what are some nice numbers we can plug into the square root function? Well, I can plug in 0. I can plug in 1, right? The square root of 1 is 1. And I can plug in 2, but that's not something I know the value of the square root of off the top of my head. And so maybe I'll just pick the next nice number to plug in. And if I plug in 4, well, I know the square root of that is 2. If I plug in 9, the square root of that is 3. And 16, the square root of that is 4. The graph of this function, right, looks like this, as we've seen. Now what about f of negative x? What does this function look like? Well, here if this is, if I call this g of x, it's f of negative x. Well, what is this? This is the square root of negative x. All right, plugging in negative x into our f function gives us the square root of negative x. And so here, if I make a table for this function, this is f of negative x. Well, what numbers can I plug into the square root function? Well, the square root function here, we don't want to take the square root of some negative number, right? Because that's not going to give us a real value out, a real number out. And so if I want to take the square root of some non-negative number, because there's already a negative sign in there for this function, I'm going to need to plug in another negative number so that those two negative signs get negated and it becomes a positive result to take the square root of. So what numbers can we plug in? Well, I can plug in 0, that's fine. I can plug in negative 1, because here the square root of negative 1 gives me the square root of 1, which is just 1. And I can plug in negative 4 to get 2, negative 9 to get 3, negative 16 to get 4. Right, something I couldn't plug in, for example, would be 1 here, because the square root of negative x, or negative, our input value, negative 1, well, this is undefined, because there's that negative sign already underneath the square root. So here, the graph of this function has a point 0, 0, negative 1, comma 1, negative 4, comma 2. Really, we get the same outputs for the negative input values. Really, what happened here when we introduced that negative sign into our f function was that it reflected this graph over the y-axis. It was a horizontal reflection. And so here, maybe let's say this more generally, is that the transformation negative f of x, when we negate the function itself, when we negate the output, this reflects the graph of f of x across the x-axis. This is a vertical reflection. Reflects the graph up and down over that x-axis. And then here, if we look at what we did just a moment ago, the transformation where we negate the input, if I have negative f of negative x, well, this reflects the graph of f of x across the y-axis. And this really amounts to a horizontal reflection. And again, it falls in line with this idea of if we adjust the input values, it's going to do some sort of horizontal transformation. If we adjust the output values or the function itself, it's going to correspond to a vertical transformation. And so here, let's take these ideas and put them together with our shifts to find an equation for this graph below. And so if you're up for it, please pause the video and give this example a try. So there's a few things going on here. Is that, well, this corresponds to an absolute value function, right? It looks like it has that V shape. So really there's a parent function, or a base function we can work with here of f of x is equal to the absolute value of x. This is not the equation of this graph here, but it's one we can transform into the one we have here. And so here, what's going on with this function? Well, it's the absolute value function, but reflected vertically. What else has happened? It's been shifted left 3 units, and it's been shifted down 2 units. And so I can think of this, to put this all together, I can think of g of x as this function here, where it's negative the outputs of my f function after we shift it to the left 3 units. So to shift left, we have 3 added to our input. And then to shift down, we subtract away 2, right? Subtract away 2. And so what does this look like? Well, this is negative the absolute value of x plus 3 take away 2. And I would definitely encourage you, if you don't feel convinced, to make a table for this function and to see that this is the right function, the right equation for the graph we have here. And so one last example I'd like to do is here I have this function f of x is equal to 2 to the x, this function outlined in black. And so here I'm telling you ahead of time that this is the equation for this function, f of x is equal to 2 to the power x, for this graph that's shown in black here. And so I want to identify the equation for g of x if I know that it's a transformation of f. So here, what transformations do you need to apply to our f function to obtain g? And so how can we use this to find an equation for this g function? So pause the video again and try this example out, again, if you're feeling up for it. So there's sort of 2 things going on here that I noticed, or that stand out to me. One is that it looks like g of x is it's almost a graph of f of x reflected over the y-axis. Yeah, that would almost be the case, right? But then well, maybe just to not clutter it, I won't draw what that would be. But it also looks like there would be a shift down 1 unit, right? So down 1 unit. And so what would that look like if g of x corresponds to a horizontal reflection? We can achieve that by negating the input, right? So here, f of negative x, and then it's going to shift down by 1 unit. So here we would have this minus 1 at the end of the day. So here, g of x can be re-expressed as well, we already know the function for f, right? We know it's 2 to the power x, so it's going to be 2 to the, we're going to input negative x into this function, and then we have minus 1. This is an equation for this function here, g of x.